Hey guys, so mm, in today's lecture, we are going to learn about buoyancy. But then before we do that, let's review a few things we did in the last lecture. Okay. So last time we learned about the fluid. Fluid is a substance that flows. We also talk about two different types of fluid, which are gases and liquids. We define another quantity called density. Density is just the ratio of mass to volume. We also found it has the unit of kilogram per meter cube. Important point to remember is that density is independent of the size of the object, meaning it does not depend on the mass of the object or the volume of the object in question. Okay. We also define another quantity called pressure. Pressure is a ratio of the force to area. SI unit of pressure is Newton per meter square, and which has a special name, Pascal, after the scientist Pascal. It is represented as uppercase P and then A. Okay, so PA. All right, that's the Pascal. Pressure is a scalar quantity. Typical 1 atmospheric pressure is about 1.013 times 10 to the power 5 Pascal. We also derive hydrostatic pressure equation where we said P2 equal to P1 plus rho GD. This equation may look different than what we did last time. Instead of P1, we had what? P naught here, right? And then plus rho was the density of the fluid, G is acceleration due to gravity, D, instead of D we had H as the depth, okay, height of the depth. And then in place of P2 we just wrote P. All right, so it's really the same equation. We also derive equation for gas pressure. Gas pressure is the difference. Gas pressure is a difference between the pressure of the gas and atmospheric pressure. Here it says P minus 1 atm. Really, if we were to relate it to the equation we derived last time, P is the pressure of the gas, and then 1 atm is just P naught or P atmosphere. Okay, so that equation gives us the gas pressure. All right. We also talk about the application of manometer, right? And manometer is what? It is an instrument to measure the fluid's pressure. We looked at one of the examples. One of the examples was what? Spigmo manometer. It measures the blood pressure, guys, and then spigmo means pulse in Greek. Okay. And then there is another picture. Probably you guys are more familiar than me when it comes to this instrument, since you guys are pre-med. Okay, so another concept we learn is about barometer. What is barometer, guys? What does it do? Does it measure blood pressure? What does it do? Okay, so barometer is an instrument that measures atmospheric pressure, and then we did derive our equation, and then we saw that P atmospheric pressure is equal to rho ZH, where H is the height of the fluid in a column right here. Okay, so this height H here. And then the atmospheric pressure, 1 atm is equal to 760 millimeter of Hg, which is also equal to 760 torr. These mmHg, atm, torr are different units of pressure, and this instrument was invented by Evangelista Torricelli in 1644. Okay, all right. So that was the revision about the last lecture. In today's lecture, I'm not going to give you guys a lot of things to do because in the last lecture I spend more time, and I think you guys had to spend like another 15 or 20 minutes extra. So today we'll do just little bit on buoyancy, on the new topic, and then just solve example problem, and then I'll let you guys go early. Okay. Okay, so where shall we start? Okay. Just a moment, guys. Okay, so new topic, buoyancy. All right. So when was the last time you have heard this word? Buoyancy. Buoyancy. Anywhere in another class, in day-to-day life, in the kitchen, in the bathroom, in the market, nowhere. Try give a reflect for a moment on this word, buoyancy. Okay, so buoyancy is buoyancy is, think about it. If you put an object in a fluid, what happens? It's going to experience something from that fluid. Okay, so that something, you could say almost like upthrust, is called buoyancy. All right, that's, again, it's not precise. This is just something I'm giving it to you so that you can kind of start thinking about what buoyancy is. Now let's say we have, and I have a picture here, pretty picture. Let's say buoyancy. So we have this small dock here on the water. This dock has a mass, which means it must be affected by the acceleration due to gravity. So that will give us a weight that's acting downward. But then there is also force from the fluid, and then there is something called buoyant force, and that's acting upward. And this is able to float it here because these two forces are acting, they are in opposite direction and balanced. Okay, so an object placed in a fluid is buoyed up by it. All right, so buoyed up by it. Okay, now here is, so what this thing, all right, it's not there. I'm gonna derive this. I hope I have it here. Okay, here it is. So let's consider buoyant. Let's see what this buoyant force is. Okay, buoyant force. We have tank here, or cylinder, whatever, filled with the fluid. Okay, and then we decide to place a cylindrical object here. All right, now this object is going to experience force, right? Before I even say that, let's see what happens to the pressure at this point. Do you think pressure is high here than comparatively to the bottom, or do you think this pressure is lower than the pressure at this point? What do you think? So pressure P increases. Okay, P increases as we go downward, right? The pressure increases as we increase the depth, as we go downward in the container, or in the swimming pool, or in the sea. Okay, so now this object is going to experience force here due to pressure in this area, and then also there is the atmospheric air here, so there is the downward force. Let's write this as FD down. But then there is also pressure here from the bottom, but then this pressure, sorry, the force here from the bottom, but this force is bigger, see, because there is a higher pressure here, this force is bigger, and this F from upward force is acting from the bottom. So there must be a net force, right? This is bigger force acting upward, smaller force acting downward, so there must be a net force that is acting upward. So this F net force that is acting upward in this case is called buoyant force, FV. All right, so the buoyant force is the net force experienced by this object when it's placed in a fluid. Okay, any question here? If you have any question, please do post it in the course discussion section. Okay, so please note that the direction of this buoyant force is upward, because this upward force is greater than the downward force, so the net force must be pointing upward. Alright, so next thing here we are going to look at is Archimedes' principle. Let me put it here. Archimedes' principle. It states that the magnitude of the buoyant force acting on an object is equal to the weight of the fluid displaced by that object. Okay, so what does that really mean? It is like this. You have a container here. Let's put a penny here. Okay, put the penny here. Then before we put this penny, let's say like this here, we have some water here, right? It is going to be in something like right over here up to this level. Okay, but then the moment we put a penny, maybe it is difficult to visualize. Let's put this thing here inside. Okay, if we had this container, big container, then oh, maybe not this thing. Let's put a penny, that's easier. Penny, I'm just exaggerating the penny here. Okay, then what happens is this is going to displace some fluid, right? So maybe that fluid level is going to rise up a little bit. Now if we were to, you know, make a hole here or somewhere, or at least pour this amount of fluid here, the one that is displaced by this penny, we collect that in some other container, and then if we measure the weight of this fluid, let's call it WF, then that weight of the fluid displaced by this object here, penny, must be equal to buoyant force acting on this penny, or the object that's in the fluid. Okay, so WF must be equal to FV. That's what it means. Okay, that's the Archimedes principle. So how can you measure the weight of this fluid in a real life? Let's say, for example, you know, I have my tea here right now. I'm not going to put a penny, guys. I don't want to drink penny. But let's say we put something here. Okay, so let's say, I don't know, what would be the easier way? Let's say we put a penny here. I'm not going to put it, but I'm just telling you. Penny here, and then what we did is we collect this amount of water displaced by that penny, you know, amount of the tea displaced by that penny in another container here. And then what we could do is we could just measure the mass of that volume of the water, right? How do we do that? At first you measure the empty container, mass of the empty container. After that you may, you know, pour the, you know, this displaced amount of displaced volume of tea on the container, and then you measure the mass of this container with the tea, and then you find the difference between the mass of the empty container and the mass of the container with the tea, and you get the amount of the displaced tea. Okay, and then that amount of then if we find that, you know, once we find the mass, we can multiply it by the g, value of acceleration due to gravity, and we can find the weight. That weight force must be equal to the buoyant force on the penny exerted by this tea. Okay. Okay, so that is the Archimedes principle here. Okay, so here are examples of a buoyant force. This picture says, you know, human head with the brain. Well, I hope there won't be, you know, human without a brain. So, well, so here, aside from joke, here we have a brain here, and then there is a cerebrospinal fluid, which is in this region, right? So the density of the fluid, or density of this cerebrospinal fluid, is actually smaller than the density of the brain. So you see density of fluid is 1007 kilogram per meter cube, density of brain is 1040 kilogram per meter cube, so they are about 33 kilogram per meter cube difference. So this brain experiences buoyant force in this fluid, okay, from this fluid. Okay, all right. So now we learned about Archimedes principle. I want you guys to figure out how to determine whether the object will sink or float. So this one, please read it on your textbook and find out how could you determine whether the object will sink or float. Okay, so this is for you to work on it later on. After we are done with the lecture, please look at this topic and find out how we can determine whether the object will sink or float. That will also bring us to this question here. So the average density of a fish is slightly greater than the density of water. How does a fish avoid always sinking? So please come up with the answer for this question, okay, after you read about sink and float. Okay, so I have my example here. Okay, so let's do one example. Okay, I'm gonna put this all the way up here. I hope you guys can see it. Okay, buoyant force. So the example goes like this. The question is, here is a pretty picture. We have an iceberg here, and then this big iceberg is actually inside the water. Majority part of it is inside the water, and then only the little bit is coming outside. So the question is, so our job is to find what volume of this object lies below this water surface. Okay, so the question, let's read the question. So only a small part of an iceberg protrudes above the water while the bulk lies below the surface. What percentage of the volume of the iceberg is below the surface? Assume density of ice equal to 917 kilogram per meter cube. Density of seawater is 1025 kilogram per meter cube. Okay, so density of seawater is slightly greater than density of ice. So here, really meaning there. Okay, first step in solving problem in physics is writing down all the given information. So let's write it down. We are given only a small part of an iceberg protrudes. Okay, we finished reading that. What percentage of the volume of the iceberg is below the surface? So let's say that the volume that is below the surface below the surface is, let's call that V dash, and then let's call it percentage equal to what? This is the question. Okay, whatever is given here in a word, I'm just translating it in the equation form, or at least in a symbolic form. That's all. Okay, so what percentage of volume is below the surface? Assume, so those are the given information to us. So rho ice, or density of ice, let me call this the density of object. Okay, so rho O means density of object, because this doesn't have to be ice, right? There could be maybe stone, I don't know, or maybe something else there. Okay, So rho naught equal to 917 kilogram per meter cube. What is the density of seawater? Instead of saying the seawater, let's make it more general. Let's call it density rho F, okay, fluid, which is given as 1025 kg per meter cube. All right. Now, okay, so let's look at this. Now, what is the next thing we want to do? Next step in solving problem in physics is, let's take this picture out. This is not part of solving problem in physics, but I'm gonna do it here, the next step. Let's make a diagram, figure. Okay, I'm gonna make this C here. You could keep going on here, but I don't want to spend time doing it. You could do it, but let's not do it right now. So let's make this iceberg. Maybe it looks like this, and then maybe this goes, majority of it is down here. Okay, like that. And then little bit is up here. So this object, this iceberg has density rho O, right? Like rho O object, and then seawater has a density rho F, okay? And then you see rho F is greater than rho naught, all right? Now, this object is in a fluid, so it must be experiencing some buoyant force, right? That must be upward, buoyant force. So if B must be acting upward, and that must be pointing upward. If it was not pointing upward, it would be, this object wouldn't be floating here, okay? So this is important thing, and then I hope after you finish reading about sink and float, you'll figure this out, okay? But then our job is to find what is the volume of this part, guys, this part here. So let's make it, what is this? That is the V dash, okay? The volume of this guy here is the V dash. Okay, so from Archimedes' principle, so let's invoke Archimedes' principle. From Archimedes' principle, we can write the buoyant force on an object Fb is equal to weight of the fluid displaced by that object, okay? So that weight of the fluid is what? Mass of the fluid displaced times the gravity, right? I'm gonna erase this, okay, here. So mass, how is this mass related to the density of the fluid? So the reason we want to find convert this mass is because we don't know what mass is. We are not given information, but we are given the information about density of the fluid. So rho F, let's say rho density is what? Ratio of mass to volume. But then for our case, we are talking about the mass of the fluid. So let's do rho F must be equal to mF by Vf, where F represents fluid, okay? So in place of this mF here, this guy are same. So what we could just write this, right? Rho F times Vf. So our equation becomes Fb equal to rho F Vf times Z. Let's call this equation 1. We can give a name. You can call Harry, I don't know, another name. You can call whatever name you like, but it's easy to do equation 1, okay? So I'm going to erase this part. I hope you guys already copied this. Okay, that is the buoyant force on this object. Okay, now this is since this object, since the iceberg has uniform density, right? Because we are given only one density for this, iceberg, right? So it has a uniform density. It has a uniform density and is floating I'm going to erase this part also, guys, except equation 1. Floating, then from buoyancy, from Archimedes' principle again, this buoyant force acting by, buoyant force acting on that object must be equal to the weight of the object itself. Okay, this is the new information here that we haven't mentioned so far. So buoyant force on an object must be equal to weight of the object itself if it has a uniform density and if it is floating. Okay, this is something new information here, so please pay attention. Next step is then what? Fb equal to weight of the object is what? We can just, instead of weight of the object, we can just do the same thing here what we did with this. So weight of the object can be written as m naught times z, but then m naught is what? Instead of m naught, we can write Fb equal to what? Rho naught v naught times z. Okay, let's call this equation 2. All right. Okay, so equation 1 is also equation for a buoyant force on that object, same object iceberg. Equation 2 is also buoyant force on the iceberg. So these two equations must be the same, right? Because they are talking about the same quantity buoyant force. So next step is to equate these two equations. Okay, so let's equate the equation. So equation 1, equating equation 1 with equation 2, we get what? Rho f bf times z equal to rho naught v naught times z. Z on the both side, we can cancel that out, and then what we do next is bf by b naught. So this bf is going here. We can write this down, and then this rho f we can take it down here. So just algebra, right? Rho naught by rho f. Okay, so this is the ratio we have here. That's not enough because we are asked what is the percentage volume, right, of the volume b dash. Okay, so we are asked what percentage of of this object is below this sea surface, right? So we said that is our v dash, but to find the percentage of this, what do we do? If we know the entire volume, which is our v naught of the object, if we know the volume of the displaced fluid, so this object must, right, this part must displace the same amount of fluid as its volume, right? What does that mean? Meaning, if you are to go in the swimming pool and you went and you got inside and you went deep down, the amount of the fluid displaced by your body would be same as the volume of your body. Okay, that's the idea. Okay, so now here, so to find the percentage, what do we do? Initial volume, which is entire volume b naught, and then the change in new volume, which is this, right, b, this part here, bf, amount of the fluid displaced, and then we take the, multiply that by 100%. So let's do this. bf divided by v naught time b naught must be equal to rho naught by rho f. It is from rho f from here, but if we multiply that 100 with 100% on the both sides, we should be able to get percentage, right? Volume percentage. So this quantity here is equal to b dash that we said at the beginning. Okay, I'm just giving this b dash percentage, just new name, that's all. Please don't worry about this symbol. Okay, b dash percentage means this is just the volume, percentage of the volume of the iceberg below the surface. Okay, so this quantity is equal to what? Rho naught is what? 900, what was the value? 917 divide by 1025 times 100%. Please calculate this value, and that should give your answer here. I'm going to leave that for you to do it. The answer should come close to, not exactly, I'm just giving you, this means close to 90%. Okay, so the saying that says something like this: the iceberg is 90% below the water seems to be correct. Okay, all right, that is the example for buoyant force.